What if I told you two guys from Texas pulled 700 horsepower from a naturally aspirated engine back in 1965, and the racing authorities got so scared they had to ban it? No turbos, no superchargers, no nitrous. Just raw, brilliant engineering that forced one of Detroit's biggest automakers to scramble and build a secret part just to keep up. This is legacy motoring, and I spend way too much time thinking about legendary engine builds and the unsung geniuses behind them. If you're someone who geeks out over drag racing history, classic muscle car engineering, and the innovations that changed American motorsports forever, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Alright, let me paint you a picture. It's a warm Texas evening in 1965. The air smells like burnt rubber and race fuel. Down in the staging lanes of a local drag strip, a Plymouth Belvedere is rolling up to the line. Nothing about this car looks particularly special from the outside. It's a full-bodied production car, white paint, stock bodywork, the kind of thing you'd pass on a highway without a second glance. But lift that hood and you immediately understand something is different. Very different. Instead of the single 4-barrel carburetor everyone expects to see sitting on top of a 426 Hemi, there are two 4-barrel carburetors, angled and crossed over each other in a configuration nobody at this track has ever seen before. The engine fires up with a lumpy, aggressive idle that sounds like it's barely holding itself together at low RPM. Other racers in the staging area stop what they're doing and stare. Some lean in for a closer look. Some take a step back. The Christmas tree counts down, the light goes green, and that Plymouth launches so hard the front wheels come off the pavement. By the time it crosses the quarter-mile mark, everybody watching knows they've just witnessed something that is going to change drag racing. And they're right. Now, you might be thinking, okay, big deal, people have been building fast drag cars since the 50s. What makes this particular engine combination so revolutionary that we're still talking about it 60 years later? Here's the thing. In 1965, making 500 horsepower from a naturally aspirated engine was considered an achievement. The fastest Cobras, the hottest Corvettes, the most aggressive factory muscle cars were working in that 400 to 500 horsepower range. Ronnie Sox and Buddy Martin were pulling 700. And they were doing it with physics, ingenuity, and a lot of trial and error in a Texas race shop without a single computer to help them. To really understand what Sox and Martin accomplished, you need to understand the canvas they were working with. Chrysler released the 426 Hemi in 1964, and it immediately became the most feared engine in American motorsport. The name comes from the combustion chamber shape, hemispherical, instead of the flat or wedge-shaped combustion chambers that most engines of the era used. The Hemi had a dome-shaped chamber that allowed for much larger valves and a much more efficient flame front during combustion. We're talking 2.25-inch intake valves and 1.94-inch exhaust valves. Those numbers are enormous even by modern standard. The bore was 4.25 inches with a 3.75-inch stroke, giving you a relatively short stroke design that allowed the engine to rev cleanly without the mechanical stress that kills long-stroke engines at high RPM. Compression ratio from the factory sat at 12.5 to 1, which was aggressive for a street engine but reasonable for a purpose-built race motor. Chrysler's official horsepower rating was 425 at 6,000 revolutions per minute, but here's what most people don't realize. That number was complete fiction. Chrysler was sandbagging, deliberately underrating the power output to throw off the competition and avoid regulatory headache. Actual dyno testing consistently showed these engines producing closer to 470 to 480 horsepower with factory calibration. Sometimes more. The engine was so dominant in its first NASCAR season that it won 37 of 49 races in 1964. 37 out of 49. NASCAR responded by banning it for 1965, which forced Chrysler to temporarily pull out of stock car racing entirely. But while NASCAR was shutting the door on the Hemi, the NHRA's super stock class was still open for business. And that's where Sox and Martin were going to make history. Ronnie Sox was the driver. Quiet, focused, and possessed of reaction times that other racers genuinely believed bordered on superhuman. He had relocated from North Carolina to Texas and built a reputation for consistency that made him dangerous regardless of what car he was sitting in. Buddy Martin was the mechanical mind behind the operation, a tuner with an almost supernatural ability to diagnose engine problems by feel and sound before any instrument confirmed them. Together they'd been competitive in Texas drag racing since the early 60s, and when the 426 Hemi became available, they immediately recognized both its potential and its limitations. The limitation was the intake manifold and carburetion setup. The stock Hemi used a single 4-barrel carburetor sitting on a manifold designed to provide a broad, tractable power band suitable for NASCAR's high-speed oval track. That's great for Charlotte Motor Speedway. It's not optimal for a quarter-mile drag strip where you need maximum power delivered in a very specific, very narrow RPM window. Buddy Martin understood that the single 4-barrel setup was essentially a bottleneck. At high RPM, that one carburetor simply could not flow enough air to fully feed those massive hemispherical combustion chambers. The engine was, in effect, choking on its own potential. So Martin started thinking about a solution, and the solution he came up with was rooted in fluid dynamics and a phenomenon called ram tuning. Here's where it gets really interesting. When an intake valve closes during the engine cycle, it doesn't just stop the flow of air and fuel. It creates a pressure wave, almost like a small shock wave, that travels back up the intake runner toward the carburetor. Now, if the intake runner is exactly the right length, that pressure wave bounces off the plenum and travels back down the runner, arriving at the intake valve at precisely the moment it opens for the next intake cycle. When that happens, the returning pressure wave literally rams additional air into the cylinder, compressing the charge beyond atmospheric pressure without any mechanical assistance. It's free supercharging. Physics doing the work that a blower would otherwise do. But here's the catch. Ram tuning only works at specific RPM ranges because the timing of the pressure wave depends on the length of the runner and the speed at which the valve is opening and closing. For maximum power at the 6,000 revolutions per minute range where Sox and Martin wanted to shift, Martin calculated they needed intake runners approximately 15 inches long. And here is where the conventional wisdom of the era completely breaks down, because a 15-inch runner on a conventional straight-down intake manifold simply does not fit under the hood of a Plymouth Belvedere. There is not enough vertical space. It is physically impossible with a traditional manifold design. So Martin did something that seems obvious in hindsight, but that nobody had actually executed on a Hemi before. He crossed the runners. Instead of running straight down from carburetor to cylinder head port, the runners crossed over the top of the engine. The left carburetor fed the right bank of cylinders. The right carburetor fed the left bank. The crossing of the runners gave him the runner length he needed, approximately 15 inches, while keeping the overall package low enough to fit under the stock hood with a small clearance modification. That crossing configuration also solved another problem Martin had been wrestling with. By positioning one carburetor over each bank of cylinders but feeding the opposite bank, the airflow velocity entering the runners was more uniform across all 8 cylinders. On a conventional manifold, cylinders closest to the carburetor tend to get a richer mixture, while cylinders at the far ends of the runners run slightly lean. That imbalance costs power and can cause destructive detonation in the lean cylinders. The cross-ram design largely eliminated this problem by equalizing the runner lengths to all 8 cylinders. Every cylinder got the same shot of air and fuel at the same mixture strength. The geometry was elegant, and honestly, it was the kind of solution that makes you slap your forehead and wonder why nobody had done it sooner, except that fabricating it in 1965 without modern manufacturing tools was an absolute nightmare. Martin spent months on prototype. We're talking hand-formed aluminum runners, carefully welded together, then cut apart and reformed when the measurements were slightly off. He didn't have a flow bench readily available. He didn't have computer fluid dynamics modeling. He had a tape measure, a calculator, reference texts on fluid mechanics, and an engine dynamometer that gave him real-world feedback after every modification. Each iteration of the manifold required new jetting for the carburetors because the airflow characteristics were completely different from anything the carburetor manufacturers had calibrated for. The fuel curves had to be rebuilt essentially from scratch. The float levels needed adjustment because the angled mounting position of the carburetors affected fuel delivery in ways that weren't obvious until you actually ran the engine under load. It was painstaking, iterative work. And for months, the results were promising but not definitive. The power was up, but not dramatically. Martin kept refining. The breakthrough came when he stopped thinking about the manifold in isolation and started thinking about the entire intake system as one continuous component from the carburetor venturi all the way to the valve seat. He adjusted the carburetor spacers to optimize plenum volume for the specific RPM range they were targeting. He matched the manifold ports to the cylinder head ports by hand, carefully blending the transition between the two surfaces to eliminate any turbulence-creating steps or lip. And he recalibrated the accelerator pump circuits on both carburetors to account for the longer time it took fuel to travel through the extended runners before reaching the combustion chamber. When he put the modified engine back on the dyno with all of those refinements in place simultaneously, the number on the gauge jumped dramatically. The naturally aspirated 426 Hemi with the cross-ram manifold was producing 585 horsepower. That was more than 100 horsepower over the stock configuration. And Martin immediately understood they weren't done yet. Now, you might be thinking, okay, 585 horsepower is already phenomenal for 1965. Why push further? Because in racing, there is no such thing as enough. And because Martin could see clearly from the data that the engine was still leaving power on the table in specific areas. The cylinder heads, even the excellent Hemi castings, had casting flash and slight irregularities in the port throats from the factory machining process. None of it was severe enough to cause problems in street use, but at the airflow speeds they were now generating with the cross-ram setup, those imperfections were creating tiny turbulent zones that robbed velocity. Martin spent 3 weeks with a die grinder and carbide bits cleaning up those ports. Not porting in the radical, material-removing sense that some engine builders use. Just cleaning, blending, and smoothing. Matching surfaces, removing casting seams, polishing the valve seats to promote better airflow around the valve head. When the heads went back on with the cross-ram manifold, power climbed to 620 horsepower. Then came compression. The stock 12.5-to-1 ratio was conservative for an engine that would only ever see race fuel. Martin pushed it to 13.5-to-1 using custom dome pistons, then to 14-to-1 with a second revision. At 14-to-1, the engine required 103-octane fuel to avoid detonation, but power had climbed to 650 horsepower. The cam timing was the final major variable. Factory Hemi camshafts were ground for a broad power band because that's what NASCAR and street performance require. Sox and Martin needed a narrow, concentrated power band centered precisely where they were going to use the engine, between 5,500 and 6,500 revolutions per minute. They had custom camshafts ground with 320 degrees of duration and 0.590-inch lift. The overlap between intake and exhaust events was so aggressive that the engine would barely maintain idle below 2,000 revolutions per minute. At low speeds it sounded ragged and unhappy, like something was deeply wrong. But at 6,000 revolutions per minute it was absolutely ferocious, pulling hard with a mechanical intensity that you could feel in your chest from across the track. With all of these modifications combined, the cross-ram Hemi was producing a verified 700 horsepower on the dynamometer. Let that number sit with you for a moment. 700 horsepower, naturally aspirated. In 1965, when a Shelby Cobra 427 with its brutal side-oiler Ford motor was making approximately 485 horsepower and was widely considered barely streetable due to its extreme power output. When the hottest Corvette you could order from a dealer made 375 horsepower and was considered an exotic performance machine. Sox and Martin had surpassed all of that by more than 200 horsepower using an intake manifold they'd essentially invented in a Texas race shop. And they'd done it within the basic framework of a production-based engine that competitors could identify and inspect without finding anything that looked unreasonable. The displacement was stock. The heads were stock castings that had been cleaned up. The block was unmodified. The cross-ram manifold was unusual, certainly, but the rules hadn't specifically addressed it yet. And that last point was going to become very significant very soon. Here's what most people don't realize about the cross-ram setup beyond the raw horsepower numbers. There were secondary performance benefits built into the design that Sox and Martin discovered somewhat accidentally during testing. The long runners, by virtue of their length and the fact that they were surrounded by moving air rather than sitting directly on hot engine components, acted as crude but effective heat exchangers. The intake charge traveling through those runners was measurably cooler by the time it reached the intake ports compared to a conventional short-runner manifold sitting in the radiant heat of the engine valley. Cooler air is denser air. Denser air means more oxygen molecules packed into the same volume, which means more fuel can be burned, which means more power. Martin estimated the thermal benefit of the long-runner cross-ram design was worth somewhere between 20 and 25 additional horsepower above and beyond the ram tuning effect. That's free power from geometry alone. Additionally, the two carburetors could be tuned and calibrated independently of each other, which opened up possibilities that a single carburetor setup simply couldn't offer. Martin developed what he called staged carburetion, a progressively linked throttle system where the front carburetor opened first during the initial throttle application. At approximately 60% throttle, the rear carburetor began opening, reaching full throttle simultaneously with the front unit just as the engine entered the peak power RPM range. This solved one of the most persistent problems with multiple carburetor setups, which was the tendency to flood the engine with excess fuel at low RPM during hard launches, causing the engine to hesitate or bog momentarily before recovering. With staged carburation, the launch was crisp and clean, the power delivery was linear and progressive, and by the time both carburetors were fully open the engine was already in its optimal operating range and pulling as hard as the physics allowed. The first time Sox and Martin showed up at an NHRA event with the cross-ram Hemi, the reaction from other competitors ranged from confusion to outright disbelief. Their Plymouth Belvedere was running elapsed times in the 10.90s at trap speeds approaching 127 miles per hour in a full-bodied production car running on bias-ply tires with essentially stock suspension geometry. Those numbers belonged in a different class entirely. Competitors started circulating accusations almost immediately. There had to be nitrous. The engine had to be stroked beyond its claimed displacement. Something was hidden somewhere, because a naturally aspirated stock displacement engine in a production car body simply could not run those numbers. It defied conventional wisdom about what was possible. After a particularly dominant weekend performance, NHRA technical inspectors at the event requested a full teardown inspection of the engine. Sox and Martin agreed without hesitation. Every component came out and went onto the inspection table. Displacement check came back at 425.9 cubic inches. Exactly stock. No hidden passages for nitrous delivery. No exotic materials that violated the rules. Nothing illegal. Just the cross-ram manifold sitting there looking unusual and somehow managing to produce power numbers that made the inspectors uncomfortable even though they couldn't find a single violation to cite. Word spread through the super stock community with the speed that characterizes racing gossip. By the time Sox and Martin appeared at the next major event, photographers were waiting specifically to document that intake manifold. Technical directors from other racing organizations were in attendance taking note, and other Hemi-powered competitors were already calling aluminum fabricators asking about the feasibility of building their own versions. The Crossram had become the most talked-about development in drag racing, and Sox and Martin had built exactly one of them in a Texas race shop with hand tools and determination. Dick Landy, another prominent and highly successful Mopar racer of the era, was running a conventional single four-barrel Hemi and losing ground fast. Landy was no amateur. He was one of the most mechanically sophisticated racers in the country and a fierce competitor. But his best runs were consistently half a second slower than Sox and Martin's worst runs. Half a second in drag racing is an eternity. It's the difference between winning every round and going home in the first elimination. Other teams began reverse engineering the Crossram concept. Some got the basic geometry right but missed the crucial details of runner length calculation and carburetor staging. An engine with Crossram induction and incorrectly calculated runner lengths actually performs worse than a well-tuned conventional manifold because the pressure waves arrive at the wrong time and work against cylinder filling rather than enhancing it. Several teams discovered this the hard way on the dynamometer, watching their power numbers drop after installing hastily fabricated Crossram setups and concluding that Sox and Martin must have some other secret they hadn't shared. The secret was the math. Martin had done the calculations correctly from first principles, and without understanding the underlying fluid dynamics, it was impossible to copy the design by eye and get the same result. But by mid-1966, enough teams had figured it out, some through their own calculations and some through careful measurement of dimensions from the Sox and Martin manifold during pit area inspections, that the Crossram Hemi had become the dominant configuration in superstock. The single four-barrel cars were being systematically outclassed. The NHRA found itself in an increasingly difficult position. The Crossram Hemis were spectacular cars to watch, and they were drawing fans to events specifically to see them run. Sox and Martin had become genuine stars of the sport, and the Crossram Plymouth was their calling card. But the rules were written around production-based components, and Chrysler had never offered a Crossram intake manifold for the 426 Hemi through any official production or dealer channel. The argument from teams protesting the design was straightforward. Production-based racing means you race what the factory builds. The factory didn't build this. Therefore it shouldn't be legal. Sox and Martin's counter-argument was that the rules specified stock-appearing components and their setup appeared stock. The visual inspection criterion could be interpreted either way depending on your definition of stock appearing. The controversy came to a definitive head at the 1966 NHRA Spring Nationals in Bristol, Tennessee. Sox and Martin had just posted a new national record, running at 10.98 at 128 miles per hour to win their class. The run was witnessed by approximately 40,000 spectators and captured on film by multiple cameras. It was, by any objective measure, one of the most impressive drag racing performances anyone had ever seen from a super stock class vehicle. During the mandatory post-race technical inspection, Dick Landy filed a formal protest specifically targeting the Crossram manifold and its eligibility under the production-based rules. NHRA officials pulled out the rulebook. 3 hours of deliberation followed, with officials consulting with technical advisors, reviewing the written rules with multiple interpretations, and ultimately having a difficult conversation about the difference between what the rules said and what they had intended to say when written. The ruling turned on a single word: production. The rules specified production intake manifolds. The NHRA determined that since Chrysler had not produced and sold the Crossram design through any official channel as a purchasable production component, it did not qualify under that definition. Sox and Martin were not retroactively disqualified. The NHRA acknowledged the innovative nature of the design and the fact that the rules had simply not anticipated it. But beginning with the 1967 season, all intake manifolds would be required to be factory production units available through dealer parts departments. The announcement gave everyone 6 months. And here is where the story takes a turn that you genuinely could not make up. Chrysler's racing division, which had been monitoring the Sox and Martin situation with a combination of corporate pride and institutional embarrassment, moved with remarkable speed after the NHRA announcement. Their own engineers had actually tested a cross-ram configuration during the Hemi's original development in 1963. Internal documents released decades later confirm this. They had seen similar power gains to what Sox and Martin were achieving. But they had rejected the design for 2 reasons. First, the tall profile of the cross-ram made hood clearance problematic on production vehicles. Second, the complex manifold would have added approximately $400 to the already substantial price of the Hemi option, which Chrysler's marketing team believed would hurt sales. So Chrysler had known this was possible. They had tested it and walked away from it. Then 2 independent racers proved it worked and built an entire winning program around it. And now the NHRA was forcing Chrysler's hand. Within weeks of the Bristol ruling, Chrysler's parts division announced the production of a cross-ram intake manifold for the 426 Hemi, assigned part number P4529068. Under NHRA regulations, a minimum of 50 units needed to be produced and made available for purchase to qualify as a production component. Chrysler built exactly 50. They priced them at $850 each, which in 1966 dollars represents an extraordinary sum, roughly equivalent to $6,000 or $7,000 today. All 50 units sold within 48 hours of becoming available, purchased almost exclusively by professional superstock racing teams including Sox and Martin themselves. The manifold was never listed in any public Chrysler parts catalog. It was never advertised in any publication. It was never produced again after that initial run of 50 units. But it was technically a production component manufactured and sold by the Chrysler Corporation, which made it legal for NHRA competition beginning in the 1967 season. Think carefully about what just happened there. 2 independent racers from Texas built something in their shop that was so effective and so clearly superior that one of the 3 largest automobile manufacturers in the world was forced to legitimize their innovation by rushing it into limited production specifically to maintain its legal status in racing. Chrysler didn't build the cross-ram manifold because they thought it was a good business decision. They built it because Sox and Martin had proven it was the fastest configuration possible, and without making it a production part, one of the best draws in their racing program would have become illegal. That is the automotive equivalent of a garage band's demo tape being so good that a major record label releases it as an official album just to acknowledge that it exists. The 1967 and 1968 Superstock seasons belonged to Sox and Martin in a way that is almost difficult to describe with numbers alone. They won 57 NHRA events across those 2 seasons, a record that survived for decades. Their Plymouth ran in the 10.80s at trap speeds consistently above 130 miles per hour at a time when breaking into the 10s in a production-bodied car still represented a genuine engineering achievement. Other teams running the cross-ram Hemi were competitive, but there was always a gap between what everyone else could produce from the combination and what Sox and Martin extracted. Part of that gap was the staging carburetion system that remained uniquely theirs. Part of it was the ceramic coating Martin had applied to the inside of the intake runners, a thermal barrier treatment that reduced heat transfer from the engine to the incoming air charge and dropped intake temperatures by approximately 40 degrees Fahrenheit. At a rate of roughly 3% power gain per 10-degree reduction in intake temperature, that coating was worth approximately 12% more power. On a 650 horsepower base, that adds up to another 78 horsepower. Free. from a coating applied to the inside of aluminum runners. Part of the gap was also the exhaust system, which Martin had developed simultaneously with the intake modifications, but which received far less attention because it was less visually dramatic. The standard Hemi exhaust headers of the era, while significantly better than the factory cast-iron manifolds, created interference between exhaust pulses from adjacent cylinders in the collectors. When two exhaust pulses arrive at a collector at nearly the same time, they partially cancel each other out, creating back pressure that resists the outflow of exhaust gases and robs power. Martin addressed this by rearranging the pairing of cylinders in the exhaust collectors, using what he called 180-degree headers where the cylinder firing intervals were evenly spaced in each collector rather than grouped as they naturally fell in the firing order. Evenly spaced exhaust pulses in the collectors created a scavenging effect instead of a cancellation effect, where the exiting exhaust pulse from one cylinder actually pulled the exhaust gases from the next cylinder out behind it. This scavenging reduced residual exhaust gases remaining in the combustion chamber at the start of the next intake stroke, which meant cleaner combustion and higher effective compression. Martin estimated the 180-degree headers were worth 15 to 20 horsepower over the conventional arrangement. Combined with all the other modifications simultaneously, the best verified output recorded from a Sox and Martin Crossram Hemi was 738 horsepower at 6,800 revolutions per minute. 738 horsepower. Naturally aspirated. 1965 technology. It's a number that remains impressive today. Now you might be thinking, surely modern engines make more power than that from the same displacement. And yes, of course they do. A modern 7.0-liter LS7 from a Corvette Z06 makes 505 horsepower from the factory, and with careful naturally aspirated building, it can reach 700 or more. But that engine uses computer-designed cylinder heads with flow numbers that weren't achievable with 1960s manufacturing, computer-optimized camshaft profiles, precision fuel injection, and decades of accumulated knowledge. Sox and Martin were doing this without any of those advantages, working from first principles with hand tools, a dynamometer, and a deep understanding of physics. The achievement scales completely differently when you account for the resources available. Here's what most people don't realize about the broader context of what Sox and Martin accomplished. The physics principles they were exploiting in 1965 weren't mysterious or arcane. They were documented in fluid dynamics textbooks. The ram tuning effect had been understood theoretically for decades before this. What was remarkable was that Sox and Martin applied those principles practically, in the real world, under racing conditions, without the computational tools that would normally be required to design a system like the Crossram manifold from scratch. They essentially reverse-engineered the physics through iterative testing, which is a form of engineering that requires both intelligence and an almost obsessive willingness to try, fail, measure, adjust, and try again. Buddy Martin reportedly destroyed or rebuilt the manifold prototype more than a dozen times before arriving at the final configuration that produced the power numbers they were seeking. That's not luck. That's methodology applied with extraordinary persistence. The psychological effect of the Crossram Hemi on the broader superstock racing community was arguably as important as its actual performance advantage. When Sox and Martin pulled their transporter into a race venue and opened the hood of the Plymouth, the reaction from other competitors was immediate and visceral. The twin four-barrel carburetors sitting atop those crossed runners, combined with the distinctive ragged idle of the aggressive camshaft, communicated a clear message before a single competitive run had been made. This car is serious. This car is different. This car is going to be very hard to beat. Racing is as much psychology as it is machinery, and there is measurable value in making your opponent doubt themselves before the tree goes green. Sox and Martin understood this intuitively, and they leaned into it deliberately, keeping the hood up in the staging lanes longer than strictly necessary, letting the crowd gather, letting the opposition look and wonder. The NHRA's tightening of the rules for 1969, mandating that intake manifolds must be available as regular production options rather than specially produced limited runs, effectively ended the cross-ram era in its original form. Chrysler was not going to tool up for mass production of a manifold that required significant hood modification to fit and served no practical street use. Sox and Martin transitioned to the Chrysler six-pack configuration, 3 two-barrel carburetors on a conventional manifold design offered on the 440 cubic inch engine and later adapted for the 426 Hemi. The six-pack was capable of approximately 550 horsepower in race trim, well below the Crossram's peak output, but it was legal, it was available through dealer channels, and Sox and Martin's deep mechanical knowledge meant they were still competitive even with the reduced power ceiling. The transition to the six-pack era also illustrated something important about the nature of racing innovation under regulations. Rules don't eliminate the drive to innovate. They redirect it. When Sox and Martin could no longer run the crossram, they applied the same methodical approach to the six-pack configuration that they had applied to everything before it. They found carburetor jetting combinations that other teams hadn't considered. They developed staged linkage systems for the 3 carburetors that improved off-the-line response. They optimized the manifold port matching with the same careful attention to airflow they'd applied to the crossram head. And while the six-pack setup never matched the outright power of the crossram Hemi, Sox and Martin consistently extracted more from it than their competitors were finding, which speaks to the depth of their mechanical understanding rather than their reliance on any single trick or component. But it's the crossram legacy that endures most powerfully, both in the specific technical concepts it introduced to drag racing and in what it represented philosophically about the relationship between independent racers and the manufacturers whose equipment they campaigned. Look at the modern high-performance automotive landscape, and you'll find the fingerprints of the crossram everywhere, even if they're not immediately recognizable. Variable-length intake manifolds, which are standard equipment on engines ranging from BMW's M-Series to Honda's VTEC designs to the Dodge Viper's V10, use exactly the same ram tuning physics that Martin calculated for the cross-ram manifold. The difference is that modern implementations use computer-controlled butterflies or sliding runners to change the effective runner length dynamically across the entire RPM range, optimizing the ram effect at low speeds, mid-range, and high RPM simultaneously rather than committing to a fixed length for a single target RPM. The principle is identical. The execution is more sophisticated because modern computing power makes dynamic optimization feasible. But the physics haven't changed since 1965, and the physics were what Martin understood and applied. The staged carburetion concept that Sox and Martin pioneered in their progressive throttle linkage system is the mechanical grandfather of modern throttle-by-wire systems. Contemporary electronic throttle control doesn't just translate your foot movement directly to throttle opening. It interprets your inputs and modulates throttle opening based on engine speed, vehicle speed, gear position, and dozens of other parameters to optimize power delivery and traction. The fundamental goal, controlling the rate at which air enters the engine to optimize power delivery relative to where the engine is in its operating range, is identical to what Martin accomplished mechanically with his staged carburation linkage. He was solving a throttle management problem in 1965 that modern engineers solve with software and sensors. The problem itself hasn't changed. The ceramic thermal barrier coating that Martin applied to the inside of the crossram runners is now common practice in professional drag racing and has trickled into high-performance street applications. Top fuel dragsters use ceramic-coated intake component. Many aftermarket supercharger kits now include optional thermal coatings for intercooler component. High-performance diesel trucks use thermally coated EGR components to manage heat transfer. The concept of managing heat as a power variable rather than just a reliability concern, which Martin understood intuitively and applied practically in 1965, is now a standard tool in the performance engineer's toolkit. The 180-degree headers that Martin developed to eliminate exhaust pulse interference in the collectors have become standard in professional-level drag racing. Any serious top fuel, funny car, or pro-modified program uses collector arrangements specifically designed to maximize scavenging rather than allowing pulse interference. Most performance header manufacturers now offer what they call tri-Y or 4-into-1 designs specifically optimized for scavenging in particular RPM ranges, which is the same engineering goal Martin was pursuing with his custom header arrangements. Here's what most people don't realize when they think about the Sox and Martin story in historical context. The 700-horsepower cross-ram Hemi wasn't just an impressive power output for the era. It was a proof of concept that naturally aspirated engines had significantly more potential than the engineering consensus of the 1960s believed possible. The prevailing view in factory racing departments was that naturally aspirated engines had practical limits well below what Sox and Martin achieved, and that exceeding those limits required either displacement increases, exotic fuels, or mechanical supercharging. Martin's cross-ram proved that the limiting factor wasn't the engine's thermodynamic potential. It was the quality of the breathing system. Feed the engine air more efficiently, at the right velocity, at the right temperature, in the right quantities, at the right moment in the valve cycle, and the potential was substantially higher than accepted wisdom suggested. That insight, which seems obvious in retrospect, was genuinely revolutionary in its time. It shifted the focus of performance engineering from brute displacement and compression to precision airflow management, a shift that defined the next several decades of racing engine development. The market value of surviving Sox and Martin cross-ram components today reflects not just collector sentiment but genuine historical significance. A complete engine from the era, documented to have been built by Martin's shop and raced by the Sox and Martin team, sold at auction in 2019 for $127,000. Not a complete car. Just the engine. One of the original 50 Chrysler-produced P452906-8 cross-ram manifolds, documented with its original serial number and paperwork, changed hands in a private sale for $34,000. These aren't just vintage parts. They're primary source documents from a specific moment in American motorsports history when two men with hand tools and deep physics knowledge changed what everybody thought was possible. When a garage shop operation forced a billion-dollar corporation to scramble and build a special production component specifically to legitimize their innovation. When the speed record books were rewritten not by a factory team with unlimited resources but by a driver with supernatural reaction times and a mechanic who could hear a pressure wave in an intake runner. There is a specific type of American story that gets told across many different domains, about the independent operator who sees something that the institutional experts have missed and proves it with results that can't be argued with. In technology, it's the garage startup that outmaneuvers the established corporation. In music, it's the independent artist whose self-produced record exposes the formula thinking of major labels. In motorsports, in 1965, it was Ronnie Sox and Buddy Martin looking at Chrysler's 426 Hemi and seeing not a finished product but a starting point. Seeing not an engine that had been optimized but an engine that had been designed for a different purpose than the one they needed it for. And having the knowledge, the tools, the persistence, and the competitive fire to transform it into something that the factory engineers who created it hadn't been able to imagine. And I want to be clear about something here, because this is where a lot of people who know the broad outlines of the Sox and Martin story miss the deeper significance. Look, the 700 horsepower number gets repeated in every article about these cars, and it should because it's extraordinary. But the number alone undersells what was actually accomplished. 700 horsepower from a naturally aspirated engine in 1965 is impressive. The method used to get there is genius. And the implications of that method, The fact that it validated and popularized an approach to intake design that became fundamental to high-performance engine building across the next 6 decades, that's what makes the Crossram Hemi genuinely historically important rather than just historically impressive. Think about the specific cascade of consequences that flows from Martin building that first Crossram manifold in his Texas race shop. The immediate consequence is obvious. Sox and Martin win a lot of races and set record. But one level deeper, the Crossram's success forces Chrysler to produce P4529068, which creates a documented production part that legitimizes the design for competition and puts those specs into the hands of every team that purchases one of those 50 manifolds. Those teams study the dimensions, understand the runner lengths, grasp the geometry, and carry that knowledge forward into their own future projects. 2 levels deeper, the NHRA's rule changes in response to the Crossram's dominance set a precedent for how the organization handles technological innovation that outpaces the existing rulebook. That precedent shapes how racing authorities across multiple sanctioning bodies approach similar situations for the next several decades. 3 levels deeper, the engineers at Chrysler and at other manufacturers who are paying attention to superstock racing in 1966 and 1967 internalize the lesson that long-runner, crossover-style intake designs produce superior power density per cubic inch, and that knowledge influences how they approach production engine design going forward. The variable-length intake manifolds that appear on production cars in the 1980s and become ubiquitous in the 1990s and 2000s have multiple lineages, but the line connecting them back to Buddy Martin's shop in Texas is real. Here's the thing about innovation in motorsports that gets lost in the celebration of specific victories and specific record. The most important contributions aren't always the fastest runs or the most dominant seasons. Sometimes the most important contributions are the ones that change how everybody else thinks about what's possible. The Crossram Hemi did both. It won races, yes. It set records, absolutely. But more importantly, it demonstrated to an entire generation of engine builders that the factory solution was rarely the final answer, that independent analysis of the underlying physics could reveal improvements that institutional inertia and cost constraints had prevented the factories from pursuing, and that the gap between what existed and what was possible was often larger than the experts believed. Ronnie Sox retired from professional drag racing in the mid-1970s. Buddy Martin continued as an engine builder and tuner for other teams, his reputation established so firmly by the Crossram Hemi program that he had no shortage of clients willing to trust him with their race engines. The Plymouth Belvedere in which so many of those record-setting runs were made has passed through several owners and most recently been documented in a private collection in the southeastern United States, still wearing its original livery, its engine bay empty of the Crossram setup, which lives separately as the museum-quality artifact it has become. The car and the engine together in original configuration would represent one of the most valuable complete drag racing artifacts from the 1960s, a time capsule from the specific moment when American motorsports was figuring out that the factory was not the ceiling, that the factory was just the floor. Now, you might be thinking, why does any of this matter in 2024, when drag racing has evolved so far beyond anything Sox and Martin would recognize that the connection feels almost abstract? And here's my answer to that. It matters because the story of the Crossram Hemi is fundamentally a story about intellectual curiosity applied to a practical problem, about refusing to accept that what already exists is the best possible answer, about doing the work, the real work, the iterative, failure-tolerant, physics-grounded work of actually understanding why something performs the way it does rather than simply accepting it. Those habits of mind don't become obsolete. The specific application changes with the technology, but the approach, questioning the assumption, calculating from first principles, testing rigorously, revising honestly, that approach is as relevant in 2024 as it was in 1965. It's as relevant in any technical discipline as it is in racing. Sox and Martin weren't the last independent racers to outsmart a factory program. They won't be the last. But they were among the first to do it so completely, so publicly, and with such verifiable, undeniable results that the factory had to respond by essentially adopting their solution. That's a specific kind of victory that goes beyond any individual race win or championship. It's the victory of a good idea over institutional inertia, of knowledge over assumption, of two guys in a Texas garage over an engineering department with 1,000 times their resources. And the Crossram Hemi, sitting in its private collection today, still carries that story in every welded runner and every hand-blended port. Still represents that moment when racing was simple enough that two people with deep knowledge and fierce determination could change everything. Still makes that argument, as powerfully as it ever did, that the best solution isn't always the factory solution, and that sometimes the most revolutionary ideas come not from the biggest building with the biggest budget, but from the person willing to do the math, build the prototype, run the test, tear it apart, and do it all over again until the dyno says what it needs to say. What's the most innovative engine modification you've ever come across? Drop it in the comments below, because I genuinely want to know what you think belongs in the same conversation as the Crossram Hemi. If you want more deep dives into the engines, the racers, and the engineering decisions that shaped American motorsports, subscribe to Legacy Motoring. We're here every week, and I promise you we have not run out of stories worth telling.